Welcome back. We are back now again. We are continuing in preparation for the examination. So exposure is key in this regard. The more questions you see is the more you will have valuable information to can confront whatever question that may arise in the final analysis. Now this is a question, that is question number 5, again on work, energy and power. So the question is saying the 2 kilogram block is released from rest. Underline the word the rest, because initial velocity there is 0. You can just write it. And then at point P, which is 5 meters above the ground, it slides down the smooth frictionless curved track PQ. Once there is a frictionless, you can underline that one, knowing that now it means that now the conservation of mechanical energy is coming into being there. So when there's no friction, mechanical energy is conserved. See the diagram below. State the principle of conservation of mechanical energy. This is a grade 10 work. Now we know it. It has got various. There's the one that is find the examination guideline will say the total mechanical energy of an isolated system. A keyword, isolated system. The word total is key, and then isolated system is also key. Then is conserved. You can say it remains constant, or it remains unchanged. Or the learner can just say the sum of kinetic and potential energy in an isolated system is conserved or remains the same. That's the option. Then 5.2, use the principle as you stated above of conservation of mechanical energy to calculate the speed of the box when it reaches point Q. Fine, we know that mechanical energy at P equals to mechanical energy at Q. For us to find that, then you are going to have, in this case, mechanical energy. There are many prescriptions there. At P equals to mechanical energy at Q. Some can use grade 12 approach and say delta EP plus delta EK, and then equals to 0. In the absence of non-conservative forces, then mechanical energy is conserved. That is another approach. You'll get the same answer. In this case now, it's a mgh plus half mv squared. That is mechanical there, and mgh plus half mv squared. Now because it starts from rest, then it will have only potential energy there. The mass of this is 2 by 9.8 multiplied by the height is 5 plus 0 equals to, at the bottom there's no height, we'll have 0 again, and then half of 2 multiplied by v squared. If you use your calculator, v will be 9.9 meters per second. Remember, in this case, please note, because we are dealing with grade 10, mass is not useful. The learner can omit the mass, or just write mm to represent the mass. Then the answer will still be correct, because they cancel out. Whether mass is 100 or 50 or whatever, the answer will remain the same, 9.9. The next question says the box passes point Q, which is the lowest point in the ramp, and moves 10 meters, that's your delta x, on a rough horizontal surface. Now we are coming to grade 12. Once it's rough, principle of conservation of energies now comes into being, work energy theorem and work done by non-conservative forces. then before striking a barrier at point R at the speed of 4 meters per second. Now we know the speed at Q is 9.9 and the speed at R is 4.4 meters per second. Use energy principle to calculate the magnitude of the average force, which is our friction here. Then we can use the very same one of work energy theorem. Then if we use work energy theorem, that's the easiest one, 5.3. It will be just work net equals to delta EK. Then we check when the object is moving along that rough surface, how many forces are acting there. We'll have gravity, that's the weight, and then the normal, and then the only force acting there will be friction. Therefore, the work net will be the work done by friction, that's the only one. Then this side will be half mvf squared minus half mvi squared. Work done by friction is the one we are calculating. Frictional force will be delta x is given is 10 there. 10 multiplied by the cosine. Friction is doing negative work. You can see the motion is going to the right, friction is to the left. Therefore, it's always anyway doing negative work, equals to half of 2 multiplied by 4 squared, which is the final, half of 2 multiplied by 9.9 squared. If you use your calculator here, you'll find that the kinetic friction will be the same as 8,2 Newton. That's how you do. You can also use work done by non-conservative force, which will be the work done by friction. Then it will give you the same. Work done by friction will be only just delta EK because there's no delta EP here. That's 5.3. Let's go to the next question. It says 5.4. Before 5.4 is a statement. The barrier, you can see the barrier exerts an impulse of 14 Newton second to the left. Yes, pushing the box backwards on the box when the box strikes the barrier. Now calculate the change in kinetic energy. That is the kinetic energy, which is from the 4 meters per second when it strikes the block, and the kinetic energy of the velocity, the final velocity after hitting the block. So then in that case, you'll have to deal with the question of saying how do we now manipulate the two in this case. Now let's go. We'll have to calculate the change in kinetic energy there because we are given the impulse. What do we know about the impulse? The impulse equals to change in momentum. Impulse equals to delta P. Fine. That is what you know so far. Now then